Okay, so last video you would have learned about pH and how we calculate that. Now we are going to look at pOH. So pOH is really similar to pH in how we calculate it. The only difference is now we are really looking specifically at that hydroxide ion, right? So pH was for the hydronium and pOH is going to represent that hydroxide ion. So pOH scale, similar to pH, also goes from 0 to 14. Okay, there are some other pieces that are similar too, and that is that 7 is still considered to be neutral. But what changes is the two other ends of the scale. Okay, now if we get something less than 7, that means it's a base. And if we get something greater than 7, that means it's an acid. Okay, so we find that the scale basically flips around. So really important when you see that you're given a pOH number, a lot of the times it's easier to think of it in terms of a pH number. And in a minute or two, I'll show you guys how you convert between the two. Because sometimes you guys see a pOH number, you're like, oh, 2, that must mean it's an acid. But when it comes to pOH, if you have 2, that actually means that it's a base. So important to recognize there are two different scales. So how you're going to calculate pOH. This looks more or less the same as how you calculated pH, except instead of using the concentration of hydronium, we're now going to use the concentration of hydroxide. So if you knew the concentration of hydroxide, you could just do negative log of that concentration. If you didn't, and you knew, let's say, the concentration of like the magnesium hydroxide or the sodium hydroxide, then you would do kind of the same steps that you did with pH. You would start by writing, in this case, a dissociation equation because most of our bases are ionic. Then we would figure out what our ratio is so that we could do our little unit analysis calculation to convert that initial solute concentration into the concentration of that hydroxide ion. So I mentioned at the beginning that if you saw a pOH number, it might be helpful to switch it over to a pH. So this equation here is going to allow for you to do that, okay? And that equation is that pH plus pOH equals 14. So if I know, for example, that the pOH was 2, I can do 14 minus 2, and that will tell me that my pH is 12. And then it's kind of a little more obvious that I am dealing with a base. So one thing you will find when it comes to these pH and pOH equations, you definitely kind of have to memorize them. They are not ever given to you. If you flip through your entire red data booklet, nowhere in there will you actually find these equations. So that does mean that ultimately you do want to memorize them because they are equations that we do also use quite a bit in Chem 30. And yeah, it's one of those, if you don't know the equation, it makes it really hard to actually be able to do that calculation. Okay, so really quick example, basically to show you how this would look. So what is the pH of a solution which has a pOH of 8.25? So givens-wise, the only given we have is that the pOH is equal to 8.25. So if we think about that equation we just talked about, we said that pH plus pOH is equal to 14. So we know what the pOH is. We want to solve for pH. So we need to rearrange this. So we get that the pH is equal to 14 minus the pOH. So we can go ahead and plug those numbers in. I'm going to do 14 minus 8.25. So when we do that, 14 minus 8, nope, that is not the right button. I still need to go to school and get my actual calculator. And that's still also not the right button. There we go, 5.75. So significant digit rules. Technically, we are doing subtraction, right? So we're looking at numbers after the decimal place. For the most part, we consider given numbers, such as this 14, to have an infinite number of significant digits, which means really I'm looking at this pOH number that I've been given. It has 2 numbers after the decimal, which is why I get to have 2 numbers after the decimal, okay? So it's pretty easy conversion, just really a matter of remembering which order you need to do things in, but basically 14 minus whichever one you have is going to give you the one that you are looking for. Okay, so let's give this example a try. So what is the pOH if the concentration of the hydroxide ion is 2.5 times 10 to the negative 5 moles per liter. And then what is the pOH? So again, we look to see what our givens are. Right now we're given that the concentration of hydroxide is 2.5 times 10 to the negative 5. So we need to figure out the pOH. So we said earlier that our equation was that pOH is equal to negative log of the concentration of that hydroxide ion. Okay, so we are going to take the number, well, I missed the negative. I always say it and then forget to type it. So we're going to have negative log of that 2.5 times 10 to the negative 5. Okay, similar to our pH, we don't have units when it comes to this, so we don't have to worry about including that. So we're going to do negative log of 2.5 times 10 to the negative 5. So we're going to get 4.60. Again, remembering that pOH and pH have those weird sig-dig rules, where only the numbers after the decimal place count for significant digits. So that means only the 6 and the 0 count. So this has 2 significant digits, aligning with this having 2 significant digits. Okay, so there is an additional part to this question. It asks us, what is the pH? We already established that to do that, we're going to do 14 minus that pOH. Okay, so one thing to be careful of when you do this is this 4.60 was a rounded number. I don't want to use the rounded number. I do want to use the entire number in my calculator, which is why I just put those dots in. So I'm going to do 14 minus my answer on my calculator, and I'm going to get 9.40. Okay, so calculated the pOH using the pOH equation, and then calculated pH simply by doing 14 minus the answer that we had gotten. Okay, so let's try something a little more complicated. So calculate the pOH of a 0.25 mole per liter barium hydroxide solution. So if we think about this, we need to get the pOH. To get the pOH, we need to know the concentration of the hydroxide ion. Right now, we don't know the hydroxide, we know the barium hydroxide, which means we're going to have to start by writing out a dissociation equation, right? Barium hydroxide is BaOH2. Okay, so we're going to have that. We are going to place it. Well, it's already technically in solution. Oh, that wasn't the arrow button. That was just a line. There we go. There's our arrow button. This is going to dissociate, and it's going to give us barium ions, so Ba2 plus Aq, and 2 hydroxide ions, right? This is why we spent time earlier in the unit and in the last unit kind of practicing our dissociation equations and our stoic or our unit analysis calculations to make sure that we could do them. So our one given is that we know the concentration of this is 0.25 moles, and that's going to be per liter, right? So if you think about it, we need to figure out the concentration of this hydroxide ion. We need to figure that out because we ultimately need to get pOH. And the only way we can get pOH is if we actually know what the concentration of the hydroxide is. So like we talked about before, we need to be able to convert the concentration of barium hydroxide into hydroxide, and we are going to do that using our unit analysis calculation. So we need to change our units to become moles of hydroxide per liter. So I have moles, but this is barium hydroxide. So like we've done before, we're going to start with that ratio. So we're going to say 2 moles of that hydroxide ion over 1 mole of the barium hydroxide. Right, so what we're looking for, what we have, we need to get rid of moles of barium hydroxide, so we're going to times by the concentration, so 0.25 moles of BaOH2. That didn't go subscript, there we go. And that is going to be per liter, okay? So now when we look at this, we can eliminate the unit of moles of barium hydroxide. That leaves us with moles of hydroxide per liter. So you'll notice in this case, we do get a different number, right? A lot of times you guys start to be like, oh, why do I have to do a ratio? It's always the same number that I started with. But in this case, It's not, right? We're going to get that the concentration is 0.50 moles per liter. Okay, now that we have that, we can go ahead and calculate our pOH, because pOH is negative log of that concentration of hydroxide, which we have now just calculated. So now we can say that this is equal to the negative log of that 0.50. So from this, we are going to get 0.30. Okay, this makes sense. Barium hydroxide is a strong base. This is a relatively high concentration. I would expect to get a very low pOH number, right? Which, if you think about it, this would correspond to a very high pH number. Because if I did 14 minus this, I'd have like 13.7, which is a very strong base, which is kind of what I would expect for this type of compound. Okay, so this one takes it a little bit further in that it doesn't give you the concentration of anything. It just tells you how many moles were dissolved in a particular volume of water, right? So we're asked for what is the pOH if sodium hydroxide is dissolved in water. So we're going to need our equations. So we have NaOH, which is sodium hydroxide. I meant to put that as a subscript. This is now being placed into water. Got a little meeting reminder there. Get rid of that. So here we can put water over top of the arrow. Okay, we're doing this time. We didn't do it last time because this is starting as a solid, and I know that because I'm given moles. Anytime I'm given moles or mass, I want to start something as a solid. Okay, this is going to give me sodium ions as well as hydroxide ions. Okay, so givens-wise, things that we know, I'll just raise that up a little bit. We know that we have 0.75 moles of NaOH, and we also know that it was placed into 0.100 liters of water. So same as before, if we are looking to get the pOH, we're going to have to get the concentration of that hydroxide so that we can actually go ahead and get that pOH. So our unit analysis this time becomes a little bit larger, right? Because we have a little bit more pieces that need to go into it. So we're still ultimately looking for the same thing as we do our unit analysis. We are looking for that concentration of hydroxide. So for that reason, we're going to start with the same thing. We're going to start with that ratio. So 1 mole of hydroxide, and that is going to be over 1 mole of sodium hydroxide. Okay, to get rid of moles of sodium hydroxide, we already have moles of sodium hydroxide right here, that 0.75. So we're going to say times 0.75 moles NaOH. We're just going to put that over liters, or not over liters, sorry, over 1, because there's no other part to that, right? So from that, I could eliminate the unit moles of NaOH. Now I have moles of OH. We need to be able to introduce that liters. So because we know it has to be moles per liter, we're going to times by 1 over that 0.100 liters. And then it places that liters on the bottom where we need it to be. So now we look at this, we wind up with moles per liter. So we do this calculation and we get that the concentration is 7.5 moles per liter. That is a very concentrated solution when we think about acids and bases. So based off of that comment, you should be expecting that you're going to get a pretty extreme pOH, okay? So we do this calculation, negative log, and I missed the negative, concentration of OH minus. So we are going to plug that number in, so negative log of 7.5. And as our answer, we are going to get negative 0.88 that we count for those sig digs, okay? So we got a negative number. This can happen, right? I mentioned previously when we talked about pH that you can get numbers outside of that typical 1 to 14 range, and that usually it happens because you have something that's really concentrated. This, when you think about acids and bases, is really concentrated, right? Normally when we're talking concentration of acids and bases, they're like something times 10 to the negative, right? And this one is definitely not a times 10 to the negative. Okay, so last example of this little package. So what is the pH of a strontium hydroxide solution if 3.60 grams are dissolved in 250 mils? So we are going to start by writing our dissociation equation. So we have strontium hydroxide. We're going to start this as a solid because we have a mass for it. So this is being placed into solution. So we'll put our arrow. We are then going to write our water over the arrow. Okay, then over here, this is going to dissociate. So we are going to get strontium ions and 2 hydroxides. Okay, so givens-wise, we have the mass of strontium hydroxide is 3.60 grams. We have the volume. Just like we talked about before, whenever we have that mass, we are going to have to go get a molar mass. So go calculate a molar mass for strontium hydroxide. Okay, so you do 1 strontium, 2 oxygens, 2 hydrogens, should be coming up with 121.64 grams, and that will be per mole. Okay. So this time it's asking us to find pH. But if I look at this equation, this is for a base. So this is where I have to be able to recognize that, sure, eventually I want to get pH, but I can't directly get that from this equation because I have hydroxide. So I'm actually going to have to calculate a pOH first, because pOH is what I can calculate for a base. And then once I have that pOH, I can convert it into a pH. And to be able to get pOH, we are going to have to get the concentration of that hydroxide. So that's going to be the first thing we need to get. Then we can get that pOH. Then we can get that pH. So a couple extra steps in this one, also a little bit bigger of a unit analysis calculation. So we're going to calculate the concentration of our hydroxide ion. Okay, so think about the units you want. You're going to get moles of hydroxide per liter. So again, none of this has moles of hydroxide, so we're going to start with our ratio. So we're going to do 2 moles of hydroxide, and that is going to be over 1 mole of that strontium hydroxide. Okay, we need to get rid of moles of strontium hydroxide. We have that in the molar mass, so we're going to take the molar mass and we're just going to flip it over so that we get moles of strontium hydroxide, oh, forgot a bracket, over that 121.64 grams, right? Now we have canceled out that unit moles of strontium hydroxide. Now we need to go ahead and get rid of that grams. So we have grams here, so we are going to times it by 3.60 grams, and then again, just over 1. Now we can get rid of that unit of grams. So now we have moles of hydroxide. All we need to do is get that liters into there. Liters needs to be on the bottom. So we're going to times by 1 over 0.250 liters. Okay, now we look at all our units, everything cancels. We're left with moles of hydroxide per liter, which is what we are trying to get. Okay, so in our calculator, I'm going to type this all in. Okay, and we are going to get that the concentration is equal to 0.2367, and that number just keeps going. Okay, so from here, now that we have that hydroxide ion concentration, we can go about calculating the pOH, right? Because we said pOH is negative log concentration of hydroxide. So we can do our negative log. Use your answer button on your calculator for this one, right? Because it is a pretty big number. There's a lot of decimal places. So we get 0.6256. Again, it just keeps going, okay? Because this isn't ultimately what the question is asking me for, I'm still not going to round for significant digits, right? Because what this question has asked me for is to solve pH. So now that we finally have pOH, we can do 14 minus that pOH to be able to get our answer. So we're going to do that 14 minus our answer. So again, use that answer button because it is kind of that gross number. And we are going to get 13.3743. So let's go back to the question. This had 3 significant digits and this had 3 significant digits. That means we are allowed to have 3 numbers after the decimal place. So 13.374 is going to be our final answer in answering this question, right? You think about it, does it make sense? Well, I had a base. I would expect that a base would have a basic pH, right? Sometimes you guys kind of get confused between the pH and the pOH and which one you need and which one you don't need. And sometimes it's helpful just to take a second and think, does this number actually make sense? Like, did I have an acid? Did I have a base? What kind of number would I expect for that pH? Or what kind of number would I expect for that pOH? Make sure you do that quick check before just assuming that everything is good.